Good day, everybody. Today I want to look at Jacobi elliptic functions as trig, and I know actually several ways to develop. This will be the first way. It's perhaps a somewhat popular way, so I'm going to look at it and then compare it to other ways of developing the elliptic functions, and some things that look different will resolve the differences there. But anyway, so to start, I'm going to have an ellipse with major axis A greater than 1 or equal to 1. But if it's equal to 1, then I have a circle. The minor axis is going to be 1. And then at any point on the ellipse, we're at xy, we're distance r away. X will be r cosine theta, y will be r sine theta. Y is always between 0 and 1, and this will end up being the Sn of u, or we pronounce it sun u. The x value could be bigger than 1, but if we look at x over a, x divided by a will be less than or equal to 1, well, between negative 1 and 1, and that will be cnu, or cun u. So in other words, x is a cun u, or cun u is x over a, sun u is y, with this ellipse. And then I've got these equations. And an ellipse gives a value of k, which will be the eccentricity, or conversely, if I start with k, it will give me the eccentricity, which will give me a. Let's look at that for a moment. The eccentricity of the ellipse with minor axis b is this, and that'll be equal to k. So we've got these equations. And conversely, I can solve for a in terms of k. So given any k between 0 and 1, I can get an a greater than or equal to 1. So k equals 0 ends up being a circle, and cun and sun then just become cosine and sine. As you go to 1, we'll see what happens. With this definition, it's kind of hard to see, but with my other definitions, we'll be able to see it better. So let's see. Let's solve for r. So there's the equation of the ellipse. 1 over a squared is 1 minus k squared, as we saw right here. So the equation of the ellipse is given by this. And if you distribute, you can then have, so I've got x squared plus y squared. I just turn that into r squared. And then the k squared. X squared is r cosine squared. So there we go. Factor out the r. And then we can solve for r in terms of theta. So this is really r in terms of theta. It also depends on k. Everything here depends on k. We usually leave it out. K is usually fixed for everything, and then theta will vary as we work with a fixed k. But for each value of k, things would change. So technically, here's our definitions. X over a will be cun u, but it also depends on k. And y will be sun u, but it also depends on k. And then r over a, we've got this new trig function. If I call it a trig function, we have this new function, dnu, it will be r over a. So if I make these definitions, and I'm doing it in terms of this u, I need to define that as well. We may have seen, if we've seen this before, we want du is r d theta, which I'll go to a little bit more at the end of this video, and then also deeply into in another video. We can kind of adjust that, but for now, we'll keep it as du is r d theta. And to be precise, I would then want u to be the integral of r, but I have to use this dummy variable, so I made it r of t. So if this is r of theta, r of t, just put a t in there. So there's r of t. So integrate from 0 to theta r of t dt, and that'll be u, and then by the fundamental theorem of calculus, du d theta is r of theta, or getting what I want, du is r d theta. And of course u depends on theta for any fixed k, so in a way it depends on both theta and k. So from these we can get the graphs. Before I do the graphs, I will look at the properties. We're dealing with this ellipse, and this is how I define cun u is x over a. So cun u y was sun u, so I've got this one property easy. If I multiply this ellipse equation by a squared, I get this equation, which I'll need at a later point. So I just wrote it here. Only gave it 1 star, 2 stars for this more important equation. From x squared plus y squared equals r squared. Well, x is a cun u, y is sun u, and r is a dun u. Quick reminder, x is a cun u, y is sun u, r is a dun u. So squaring, then dividing by a squared, and of course 1 over a squared is 1 minus k squared, the way we defined k. So distributing, I get cun squared plus sun squared, which will be 1. So I've got this identity right here. It's another important identity. So again, here we are an ellipse. This one has major axis 5/3. K is 0.8, minor axis 1, at any point xy. The y value is sun. The x value, well, since cun squared plus sun squared is 1, those 2 points are always on the unit circle. And since I know the y value, then just go to the unit circle and I'll get the cun value. It'll be this. So in the graphs I look at below, I'm going to use k equals 0.8, a high eccentricity, so we can see some of the things. Not too high, though, as we'll see. But that leads to the major axis of being 5/3. Minor axis is 1. I see I've already got this capital K, not to be confused with little k, although it's dependent, but this will be the quarter period of the graphs if you integrate from 0 to pi over 2 of r of t dt. So in this case, it's almost exactly 2, which is kind of convenient. And so if that's the quarter period, then the full period will be 8. All right, so here's the graph, at least from 0 to pi over 2 of r of t, or r of t. And that leads to this graph for u. Here we can visualize it. So as I let theta increase, the upper bound right here, u is that integral from 0 to theta, so the area under the curve. So there we go. The old fundamental theorem of calculus to make a new function. So we can get u in terms of theta pretty easily. And there's the graph from 0 to pi over 2. We don't have to stop at pi over 2. The integrand is right here. It's going to have a period of pi. And so you can see the area from 0 to pi over 2 will equal the area from pi over 2 to pi. So I'll just get double. So there's u in terms of theta, and if I stop at pi over 2, well, we're not reading the u value here, but it's about 2. And then as I go to pi, I'll get about 4. And I think we get the idea, but you can just keep going and going forever. So here I go to 2 pi. So there's the integrand, and again, it's pi periodic, so you can keep going. So at this point, u is, in terms of theta, is pi periodic. All right, so if we can graph u in terms of theta, here's the idea. So u in terms of theta, again, if I just want to graph it, I can just let x equal theta, graph it parametrically, and then y be the formula for u. So y is u, this integrand, and x is theta, and then I'll graph u in terms of theta. And, well, if I want to graph theta in terms of u, which is actually what we want theta in terms of u for our graphs, then parametrically, all I have to do is let x be u and y be theta. Just switch the x and y in there. You've got the graph of theta in terms of u. It's 1 to 1, so it does have that inverse, and it's all easily solvable. From here, for the graphs, we can just use the definitions. Con u is x over a, but x is going to be r cosine theta. And what was r? R was 1 over the square root of 1 minus k squared cosine squared. So, and then I'll put it all in terms of k. So 1 over a squared is 1 minus k squared. So 1 over a is that square root. So here I have con u in terms of theta. So then if I want to graph, I'll just graph u horizontally. So x is u, and then y, right, is con u, both in terms of theta. And if I want to graph sun u, it's just y. Well, y is r sine theta, so it'll be this. And then for the graph, let x be u in terms of theta. Y will be con u in terms of u of theta. And then done u, which we'll see its importance in the future, but for now we'll just define it here as r over a. So notice it's always smaller than 1, because the biggest r can be is a when we're at the major axis, and then once you leave the major axis, r gets smaller than a, and it goes as small as b. So the minimum will be b, which will occur at pi over 2, which here I've put in terms of the period. So we could see these graphs are, the period is 4k. Maybe look at what's going on here. So as I'm on the ellipse, con u is x over a, sun u is y. So for any point on the ellipse, there's the sun is just the y value. And then since sun squared plus con squared is 1, I know the point has to be on the unit circle, and or positive, so it'll look like that. So this amount, this horizontal amount is con u, x over a. This vertical amount is sun u. And here's u in terms of theta, right? So I know what u in terms of theta is just by that integral. And so I can let theta run, and not just 0 to pi over 2, but you can just keep going. Notice r over a is 1. Here we are at theta equals pi. So y is 0, and x is negative a. So con u will be negative a over a, or negative 1. So I can go around. So that's why it's 4k periodic. Right, so as theta goes 0 to pi over 2, u goes 0 to k. And then here we are, theta is between pi over 2 and pi, but u is between k and 2k. And so it's similar to sine and cosine. Period will be 4k, because it's in terms of u. And if we look at these graphs, a translation of sun will not give con. You can see they're different. These are for the same value of k equals 0.8. So translating sun will not give us con. But it turns out con, cn of u, divided by dn of u, done. So Cn divided by dn is a translation of sun. So if I shifted this k units to the left, it would be the same as cun divided by dun. On a unit circle, cun will be cosine, sun will be sine, and dun will just be the number 1. And capital K would be pi over 2. Here I can see theta in terms of u for different values of k. So there's the rule. If k is 0, then this integrand's 1, and u is just theta. So it's a straight line, u equals u, theta equals u. But as I increase k, then it deforms a little, not too much at first, but let's see if we go to 0.8, here's around 0.8, so that's what I'm dealing with. It'd be a little closer like that. There's some trouble. As k goes to 1, this integral wouldn't be defined, so that'll be different with a different definition. You might have seen one with a sine squared here, and we'll unite those two different approaches later. But they are different integrands, so you'd think they would give different results, but we'll see. One good thing, though, about the sine is I can integrate when k is 1, whereas here I can't really integrate as k equals 1. You can do some limit stuff. I'm not going to go through the details right now. Maybe I will in another video, but we'll kind of look. I did have to stop this so as k goes to 1. I mean, you get into trouble. So I had to stop it at like 0.999. So that's theta in terms of u. And then, of course, related u in terms of theta. This would be the easier one to do. Maybe I should have looked at this one first. So this is directly from that integral. And so it's the same graph, but I just, parametrically switch the x and y. It's easy enough to do. Here's cun u for k equals 0. Should be cosine. And as I increase k, it seems like too much happens, but I mean, it's no longer a cosine graph. And then as k gets closer to 1, you can actually see we actually kind of have concavity change, not just at the intercepts. So, but this would be the graph of cun for different values of k. One thing, as I mentioned, we'll eventually see is it's going to approach. So as k goes to 1, we can't. It's harder to see with this definition, but it approaches hyperbolic secant of u. So here's cun u, and here's hyperbolic secant of u. Let's go to 0.999, and so the closer k, I called it kk here for cun of u, it's converging to the hyperbolic secant of u. So kind of interesting. And again, here's cun u at k equals 0.95, and I did find the where the concavity changes, the inflection points. So you have extra. You always have inflection points at the u-intercept there, but we also have some at other points, and they start to appear when k is bigger than root 2 over 2. At root 2 over 2, that's when it's first become defined, but they're at the intercepts anyway. So once k is bigger than root 2 over 2, up to 1, and at 1 it converges to, I forget the y values like root 2 over 2, and the x values natural log of 1 plus root 2. Here's sun u. So at k equals 0, it should be sine, and then as k gets bigger, it gets more and more distorted. Looks like so. And as k goes to 1, it'll approach hyperbolic tangent of u, which is in blue. So if I put so as k gets closer to 1, the graph converges to hyperbolic tangent of u. And here's done u. So at k equals 0, it's 1. And as k gets bigger, notice it's r over a, so it's always going to be positively valued. But it goes to, I think it converges to, what does it converge to? Hyperbolic secant as well. Now there are 9 other functions if I take reciprocals. So 1 over sun u, 1 over cun u, 1 over done u. Those you would switch. So from dn, you just make it nd. So if you switch it, 1 over sun would be ns. And if you divide, so like sun u divided by cun u, it's s over cu. And as I mentioned, cun u divided by done u, that's this one right here, that'll be the same as sun u, but shifted over 1 period, k. So there's 12 total of these functions. But the main 3 we've looked at. Definitions of the other 9 too. It was Dr. Schwalm, I think I got that, who mentioned this, although I believe he said he learned it from one of his instructors. But anyway, I'll reference in the descriptions. So let's find the derivative of sun u. We're going to use our definitions that I rewrote right here. Notice that any x, y, x is r cosine theta. And I guess I'll need it in a moment. So cosine is x over r, or secant, 1 over cosine would be r over x. So what he does is he looks at tangent is y over x. Take the differential of both sides. So differential of tangent will be the differential of y over x. Kind of a multivariable differential here. So there's kind of 2 ways to do it. You can either do the quotient rule, which I actually did first, or I thought, well, you could also just take the differential. So it'll differential of the right-hand side here. It's partial y dy plus partial x dx. Might want to do it in the other order, but so partial y is 1 over x dy. Partial x will be negative y over x squared dx, or quotient rule. So either way, you'll get this. Differential on the left will be secant squared d theta, which, since secant theta is r over x, I can put that in there. Take the multiply both sides by x squared, then divide by r. That'll leave me with an r d theta, which will be our du. So multiply by x squared, divide by r. So now I have this. And I want things to get d sun u du. I really want dy du. So I'll get rid of this dx. We'll go back to the equation of the ellipse. Take the derivative of both sides here. We'll get 2x over a squared dx plus 2y dy equals 0. So I guess it's kind of a differential there. So solving for dx, yeah, I just cancel the 2's, move the y term over, flip, multiply. So we've got dx in terms of dy. And now, so r d theta is x over r dy minus y over r dx. And I can sub in what dx is, then it's that dy. So then I can factor out the dy, and x squared plus a squared y squared. That's where I needed this property, multiplied through by a squared. That numerator is just a squared. So this becomes a squared over xr dy. The r d theta is du, as we said. So if I look at dy du, it's xr over a squared, or x over a times r over a. But again, dy du is d sun u, and x over a is cun u, and r over a is done u. So there's the derivative. And then we can get the derivatives of the other 2 from the identities, cun squared plus sun squared equals 1. Take the derivative 2 cun d-cun du plus 2 sun d-sun du, which we just found up above. You can plug it in. You can solve for this unknown derivative, divide, and we get that. And again, we can get done u from the other identities, right? So from our two identities, we can get these derivatives. Just take the derivative here, minus 2k squared sun times derivative of sun equals 2 done derivative of done, which I want to find, divide, and we got it. So those are the important derivatives. If you didn't like that way, and I wanted to see another way, I did redo it more directly from my more precise definitions. Instead of du is r d theta, I have u is this. Of course, which implies du is r d theta. Sun u is y, which is r sine theta, but r is 1 over this square root. So that'll be sun. This will be cun. R cosine r divided by a, though, puts this at the top. And there's done u is r over a. So r is 1 over, divided by a is multiplied by this square root. And that's how I got the graphs. So looking at the graphs, I can get dy du will be dy d theta over du d theta. And have it here. It's just simple quotient rule. Derivative of the top times the bottom minus top derivative of the bottom all over the bottom squared. Boom. And then du d theta is easy enough. Fundamental theorem of calculus, just plug theta into there. Flip and multiply. So this square root becomes, it's square root squared now, so it'll be cosine theta times that, minus, and then when I multiply this square root, it'll cancel with this to the minus 1/2 when I did the derivative of the bottom before. And combining things, it becomes that. You can factor out cosine. K squared can be factored of cosine squared plus sine squared theta, which is 1, so I really have 1 minus k squared cosine theta. And I can split this into a product with square roots, which then shows it's cun u done u. You don't need to see, then the other two follow from the identity, so I don't really need to redo them. I'll just quickly show you. I did this because I wanted the inflection point, so if I want the inflection points, I ended up needing this, so I did do the work. So you do have to visualize things, right? So I kind of want to think, I can't help but do dy du is dy d theta. Well, I really want dy dx is dy d theta over dx d theta. So I wanted y to be, we're thinking of the graph now. When I graphed y equals cun u, where u is in terms of theta. So there's how I did the graph earlier. And the horizontal, the x was u, so it'd be like that. So for the graph, if I have x and y like so, to graph it parametrically, then dy dx will be this, which will give me d cun u, because I'm graphing cun u. And then quotient rule again. I'll just leave this if you want to look at it in the description. You can print off as a PDF. But ends up being this, which gives me the same thing as before. Again, that led to the second derivative, which I'm just going to zip through kind of quickly. And you either get cosine theta is 0, which occurs at the odd values of k, capital K, the u-intercepts. And also, you get no solution until this quantity is less than or equal to 1, which occurs when k is at root 2 over 2. And at root 2 over 2, if you look at the graph, it'll be right at the intercept, but then as k goes bigger, it deviates. There, you got all the work. Yeah, I was going to do this later. Let's see. Yeah. So, there's that value. think I'll do these more later. So again, what I'll do in the future is I'll compare with the standard definition. So here's the standard definition. I'm going to look at it 3 times, but they just use m for k squared there. If I have it. And that's a different integrand. So it should make a difference. This integral, and if you solve for r, so this is not r of theta. Just rewrite it over and over. Here they have x instead of u. Couldn't find a good thing which used the same notation I did all 3 times. I'm going to look at some good generalizations, different generalizations. So besides that standard definition, just something that's kind of interesting. If you do a more generic ellipse, we still have the horizontal as the major axis, but I don't restrict that b has to be 1. So b can be bigger or smaller than 1. I just need a bigger than or equal to b. Here I drew both of them bigger than 1. And we'll see what happens. I mean, it's mostly the same. I guess I'll mention quickly kind of one important thing is u isn't r d theta anymore. So I'll go into that a little more. Instead, if you solve for r, it is this. So r divided by b is this quantity. And if I look at the average value of r over b, so here's r over b, which before was just the integrand, which was r. So this is the same shape as before because I kept the eccentricity as 0.8. But instead of being 1 and then 1.67, it's in terms of b. So if you graph that, then it's dimensionless. And if I look at the average value of that, then u is then the theta we're at times the average value. Because the average value, you can kind of see these thetas will end up canceling, and I'll just get this integral, which is the integral of r over b. So there was a lot of people wondering, what to make of that du is r d theta. It's really not r. It's more dimensionless. But when b, the minor axis, was 1, it disappeared. So I'll go into that a little more, and then the point on the thing. Anyway, so I'll go into different ways of looking. Also, what happens if you have the major axis vertical instead of horizontal, with or without 1. I'll probably mainly just do with 1 here, but then you have to change things. So there's kind of different ways to develop the kun, sun, and dun. If you're not careful, you'll get different things, and it could look like things are different when they're not different, and so forth. So I'll go into all of that. I'll go into the concavity more, perhaps. The limits as k goes to 1. It's a little better with the other definition, where I've got a sine squared instead of a cosine squared. And then I'll go into the differential equations. That once you've got sun and kun and dun, then there's these differential equations they solve. And they're very important. And also solving the pendulum. So hopefully this made some sense, and you watch the other videos to get a complete idea of the Jacobi elliptic functions. Anyway, thanks, and have a good rest of your day.